Okay, so get this, right? We are diving deep, deep into the world of artificial neural networks.
ANNs.
ANNs, you got it. And let me tell you, the stuff you sent over, it's like, whoa. We're talking machines learning like us, all thanks to these amazing Nobel Prize winners in physics this year.
It really makes you think, doesn't it? It's not just physics making computers powerful anymore. It's using physics to, like, figure out learning itself.
Right. Taking cues from the most complex thing we know, our own brains, and turning that into code, that's seriously mind-blowing if you really think about it. But you got to admit, sometimes I feel like we toss around machine learning without really, explaining it. It's one of those buzzwords.
Totally. Boiled down, machine learning is all about finding patterns in data. Think about how you learned what a cat is. You saw enough of them, your brain's like, okay, got the key cat features.
Right, makes sense.
Machines, we can train them to do the same, but with way, way more info.
Gotcha. So where do these artificial neural networks come in?
The name's a giveaway. Scientists, they looked at how our brains are wired, neurons, synapses, the whole shebang. Each neuron's linked to tons of others, and when we learn, those links change, right? Get stronger or weaker, and that's how info flows differently.
So ANNs, they're like trying to copy that, but in a computer.
You got it. In an ANN, we got these artificial neurons, we call them nodes, and the connections between them, those are like synapses. By messing with how strong those connections are, we can train the network, recognizing patterns, making guesses about the future, even making new data.
Whoa, hold up, making new data. So not just knowing a cat in a photo, but like AI creating its own cat pics from scratch.
Kinda, yeah. But before we get ahead of ourselves, gotta rewind a bit, talk about the OGs, John Hopfield, Geoffrey Hinton, our Nobel folks. Back in the 80s, they flipped the script on how we see machine learning.
The 80s, okay, so big hair, synth music, and the birth of ANNs. I am here for it.
Well, it actually all started way back in the 40s when scientists were just figuring out how those brain networks even work. Hopfield and Hinton, they were physics guys, used that knowledge to make the first, math models of these crazy, complex biological systems.
So biology sparked the idea, but physics made it happen.
That's so cool. Though I did read somewhere that ANN research, it kind of hit a wall for a while. What happened there?
You're right. 60s, 70s, things slowed down. The tech just wasn't there to do much. But then, boom, the 80s hit, and Hopfield drops this bomb, associative memory.
Associative memory. Okay, got to break that down for me. What is it and why is it a big deal?
Okay, so picture this. You're trying to remember a word. It's right there on the tip of your tongue, but other words keep popping up instead. Frustrating, right?
No, tell me about it. Happens all the time.
Well, that's kind of how Hopfield networks work. Get this. They can store these patterns, and then even if you only give them part of the info, they can, reconstruct the whole thing.
Okay, so, if I see a picture of a cat, but its tail's cut off, I still know it's a cat, not a dog, right? Exactly. Your brain's filling in the blanks based on what it's learned about cats.
Right.
So Hopfield, he used this idea called energy landscapes. Pretty wild stuff. Imagine a ball rolling down a hill. It's going to end up in the nearest valley.
Yeah, it makes sense because that's the lowest point, energy-wise.
Exactly.
Yeah.
So in a Hopfield network, those valleys, those are the stored patterns. Even with a messed up input, the network can still find the full picture in its memory. It just looks for the closest energy valley.
Okay. So it's like all these memories are like valleys, and when you give the network new info, it's like rolling a ball. And that ball's going to naturally go to the valley that's most similar, even if the info's incomplete.
That's a great way to think about it.
Okay, that's seriously cool.
Yeah.
But how do we actually use that? What's the real-world application of this whole energy landscape thing?
A really cool example, image restoration. You know how Photoshop can, fix a blurry picture or get rid of something you don't want?
Yeah, that's like magic.
Right. Well, it's using associative memory, just like a Hopfield network.
Whoa, seriously. So understanding how these networks remember stuff can help us actually reconstruct missing info in real life. Never thought Photoshop was using such complex math behind the scenes.
It's wild, right? And it's not just for pictures either. Same idea works for sound cleaning up old recordings or even predicting missing data points in a set.
Okay, my mind is officially blown. So Hopfield, he was all about associative memory, these energy landscapes. What about Hinton? What is his big contribution?
Hinton, he took inspiration from a totally different area of physics, statistical mechanics. Think about the molecules in a gas.
Okay, vaguely remember that from school. Lots of equations, probabilities.
Right. But stick with me here.
Okay, I'm trying. I am.
So what Hinton realized, right, is that you can use that same statistical approach to build a machine that doesn't just recognize patterns, it generates new ones.
Wait, hold on. You're saying we can teach a machine to be creative.
Not like conscious thought or anything. It's about understanding how the data is structured at its core. He called his creation the Boltzmann machine. And just like those gas molecules, it uses probability distributions to represent info.
Boltzmann machine. Got it.
Oh.
But how does it actually work? Like, give me the behind-the-scenes look.
It's all in the structure. Remember those nodes we talked about, the artificial neurons?
Yeah.
Boltzmann machines, they take those to a whole new level.
Okay, now I'm really intrigued. What do they do? Okay, back it up a sec. We get these Boltzmann machines, right? And they're pulling inspiration from, like, gas molecules bouncing around. What's the big deal with how they're structured?
It's all about layers, think layers.
Yeah.
Boltzmann machines, they've got these visible nodes, right? That's the data we feed in, like those cat ticks we were talking about. But here's the wild part. They've also got hidden nodes. These guys, they aren't getting fed data directly. They're working behind the scenes, you could say.
Hidden nodes. Okay, now it feels like we're going deeper into the matrix here. What are these hidden nodes doing?
Okay, imagine a magician. Yeah. You see the rabbit, poof, out of the hat, but you don't see all the gears and tricks making it happen.
Right. It's all hidden.
Exactly. Hidden nodes, they're like adding more magic, more complexity. The machine can pick up on way more intricate patterns, the connections in the data.
So if visible nodes are like the magician showing us the rabbit, these hidden nodes are like the secret trapdoors and levers doing the real work. But instead of a rabbit, we get, like, insights from the data.
You got it. And just like training a magician takes time, to train a Boltzmann machine, you got to show it tons of examples. It tweaks the connections between those nodes, visible and hidden, until it's crazy accurate, picking up even the tiniest patterns.
So we're basically coaching our Boltzmann machine to be a master magician. It's fine-tuning its act, getting those hidden mechanisms just right so it spots a cat no matter what, even a shadow puppet.
Love the analogy. And that's what makes Hinton's work so groundbreaking. He didn't just stop at one layer of these hidden nodes. He figured out how to stack them, creating these deep neural networks. And that, my friend, is how we got deep learning.
Okay, so from shallow networks to deep learning. Sounds like those extra hidden layers really supercharge things. But isn't training something that complex, I don't know, like herding cats, robotic cats at that?
Oh, it was a huge hurdle. But Hinton, he had a breakthrough. Remember those energy landscapes from Hopfield's work?
Yeah, like the ball rolling down the hill to find the right valley.
Exactly. Hinton, he used a similar idea but made it even better. Developed a more streamlined Boltzmann machine called a restricted Boltzmann machine. This new version was way easier to train, and he figured out he could use it to pre-train each layer of a deep network separately.
So instead of overwhelming this massive deep network with all the data at once, he gave each layer its own little training session.
You got it. Each layer, it learns the basics, like recognizing edges in an image, before passing the info on to the next more complex layers. Like, you got to learn your ABCs before you can write a novel.
Right, like building one of those human pyramids. You wouldn't just tell everyone to jump in at once. Got to build it layer by layer for it to work. And that's what led to all this amazing deep learning stuff we see everywhere today.
Absolutely. And it all goes back to that deep understanding of physics, right? Those brilliant minds connecting the dots. Now, AI is writing code, composing music, because these deep networks can handle incredibly complex data.
It's kind of poetic, actually. We started with scientists trying to understand our own brains, and now AI is writing poetry, diagnosing illnesses, even driving our cars.
It's a two-way street. Now, we're using ANNs to push the limits of physics research itself, analyzing particle collisions, cooking up new materials, even helping us wrap our heads around black holes. It's like physics gave birth to AI, and now AI is returning the favor, helping us unlock the universe's secrets.
Full circle. What a ride this has been. We've gone from the structure of the brain to the future of AI, and it's all thanks to these amazing Nobel Prize winners.
Yeah.
Seriously makes you realize how connected science really is.
Right. It's a good reminder that there's always something new to discover. And sometimes the biggest breakthroughs come from looking at a problem in a totally new way, just like those pioneers did back in the 40s.
And that, my friends, is what the deep dive is all about. Exploring a topic, going deep, deep down, and coming out with a whole new perspective. Thanks for joining us on this journey. And until next time, keep those brains buzzing, and we'll keep bringing you these deep dives into, well, everything.